Welcome everyone to this second session of the webinar series on water resources and environment at Universidad de Chile. Before we start, with the presentation, you can ask your question in the chat, and Dr. Mendoza will ask them to Dr. Neupauer after her presentation. My name is Nicolás Vázquez. I'm a PhD candidate at Universidad de Chile. We are very, very happy to have Dr. Neupauer here with us today. Dr. Neupauer is a professor and President's Teaching Scholar at the University of Colorado Boulder in the Department of Civil, Environmental, and Architectural Engineering. She received a Bachelor in Civil Engineering from Carnegie Mellon University, a Bachelor in Spanish from the University of Colorado, a Master in Civil Engineering from MIT, a Master in Math, and a Ph.D. in Hydrology from the New Mexico Institute of Mining and Technology. And her research focuses on groundwater flow and transport modeling with applications to groundwater remediation, stream depletion quantification, subsurface hydrology in frozen and partially frozen ground, and protection of water supplies and groundwater dependent ecosystem from chemical and thermal contamination. Dr. Neupauer is a fellow of the Geological Society of America and the Environmental and Water Resources Institute of the American Society of Civil Engineers. So, Dr. Neupauer, thanks again for being with us today. The floor is yours.
Okay, thank you. It looks like I can't share my screen, so can somebody enable me to share my screen?
Okay, hold on.
Okay, I think you should be ready to go.
Okay, got it. Okay, so yeah, thank you all for coming, and thank you for inviting me to do this presentation. I wanted to start out by saying I have been to Chile a few times, and I think it's a beautiful country. I have a map here. These red lines on the right show where I have been, and I did some bike trips that extended into Argentina, and the yellow is where I'm going in January, so I'll be back, and I'm looking forward to that as well. And then the map on the left that shows where I'm from Boulder, Colorado. Before I go into my presentation, I just want to upfront acknowledge some people. So I have some current and former students whose work I'm presenting today, and then some models and codes that were provided by the USGS and the Budapest University of Technology and Economics, and the USGS funded most of the work I'm going to talk about today. Well, I'll start out with some motivation. The topic is stream depletion, so I'll talk about why we care about stream depletion. I'll give a definition of what stream depletion is, some overview of estimation methods that we use to estimate stream depletion, and then some of the recent advances that have come out of my work and the work of my students. So we'll start with motivation. What I'm showing here is a picture of a river and an irrigated field. And the irrigated field, if it uses groundwater for irrigation, is going to lower the water table. Some of the water will come from the aquifer beneath the field, but some of it will come from the water in the river. So the river flow rate will be decreased as a result of pumping when you're pumping from an aquifer nearby the river. And what might happen, I'll show you in a picture here. This is going to be from the Middle Arkansas subbasin in Kansas. So I highlighted Kansas in red on the right, and the location that we're looking is in central Kansas. You can see the green on the map at the kind of the middle of the screen. And here's a picture of the Arkansas River in July of 2001, and then also again in May 2005. So this is in an agricultural area, and in July 2001 there was a lot of water in the river. Then over time the water's pumped, there's probably a less precipitation, so the water level in the river went down, but but pumping essentially pumped the river dry. And this is what we want to pay attention to when we talk about stream depletion. So we want to make sure that there's always enough water in the rivers to support the needs of the river, even if there are pumping wells operating nearby, pumping groundwater out of the aquifers. Next, I'll talk about the definition of stream depletion in both in words and equations. So here I'm showing two aquifers, or the same aquifer really, two different states. The one on the left, we have a river. You're looking at the aquifer at the bottom in gray. Water's flowing in the river at that flow rate Q sub R. And the blue line right here is the water, is the potentiometric surface of the aquifer. And there's going to be some exchange of water between the river and the aquifer because the river has a higher stage than the water level in the aquifer. So we get some exchange across the sediment, and that's that Q sub S. The one on the right is the same location, except now there's a pumping well, and the pumping well is pumping water out of the aquifer. That lowers the water table to the new solid blue line here. And because of that, there's now a larger head difference between the head in the river and the head in the aquifer. So we get more exchange between the river and the aquifer. So that QS, the arrow now is bigger. So there's more exchange. And that means that whatever flow rate there was in the river is now reduced because of that additional, because of pumping has created an additional exchange of water with the aquifer. That's what we call stream depletion. So the amount of water, the change in that Q sub S due to pumping is what we call stream depletion. And we have some, in my part of the country, in my part of the United States, most of the states have water rights where some people are entitled to water. The first people to use the water historically are the first people entitled to water. And typically we think of that as those as surface water rights, but because with these pumping wells, they're actually extracting some surface water, they also control the amount of pumping that you can do. And the relationship shown down here is just a general relationship that you can pump at some rate Q naught as long as whatever your state dictates the proportion is, alpha times Q naught is less than the amount of change in the exchange between the aquifer and the river, or the amount of stream depletion. So in Colorado, where I live, it's very small. We could pump in a well without that's not subject to water rights, as long as the pumping, the stream depletion is less than 0.1% of the pumping rate after 100 years. So this alpha in our case is 0.001. Other states have other values, and some are greater than that. So you could pump at a higher rate. But that's the driving force behind the stream depletion. So I want to also present a mathematical equation, because then the rest of my talk will use that as we look at some of the simulations. So what I'm showing here now has a little bit more math to it. The picture on the left, I'm showing H naught as the head in the absence of pumping. HR is head in the river. W is the river width. B is the thickness of the sediment. And you can see the equation below that that's representing the exchange of water between the river and the aquifer. It's equal to the integral along the river length. So the S here is the length along the river. And what's inside there is essentially Darcy's law. So we're looking at the head difference between the river and the aquifer, multiplying that by the hydraulic conductivity of the river sediment, that's that K sub S, the river width, dividing by the thickness of the sediment. And that will tell us what is the exchange between the river and the aquifer. This should actually be H naught. Then the change in stream depletion, the change in that Q sub S, which is the stream depletion, so delta QS, is that same thing with pumping. So that's this part right here, minus what we have without pumping. And if we define the head difference between the initial head without pumping and the head with during pumping as this drawdown phi, then we could write stream depletion in a much simpler way. It's this C, which we call conductance, which is just properties of the stream bed. So the hydraulic conductivity of the stream bed sediment times the width of the stream divided by the stream bed thickness, multiplied by that drawdown, and we integrate that over the length of the river. And that will give us the total change in the flow rate across the river sediment, or by definition, stream depletion. So there are several ways to estimate stream depletion. There are some analytical solutions. Actually, there are many analytical solutions. There's a numerical approach that is something that can be done regardless of the geometry. The analytical solutions all require special assumptions. And then the adjoint approach, which is something that has a different point of view, and that's what a lot of my work is based on. But I'll go through each of these just to give you the flavor of what they are, and then we'll move on to the advances. So there are two really common analytical expressions for stream depletion. The Glover-Balmer and Glover-Balmer at the top is the most simplified version of the aquifer river system that you could imagine. So on the left, I'm showing the plan view. The river is the river runs straight from in the direction of the y-axis from infinity to negative infinity. There's a well that's a distance L from the river, and the picture in the middle at the top is showing the side view of that. So we have a homogeneous aquifer. We're pumping out of that, and the river is fully penetrating. This is about the most simple case you can imagine. And Glover and Balmer in 1954 came up with an expression for stream depletion in that scenario. And that's shown here at the top right, the equation delta QS, so the stream depletion normalized by the pumping rate is equal to the complementary error function of what's shown inside there. S is the storage coefficient of the aquifer, T is transmissivity, and little t is time. This is the largest value, the largest amount of stream depletion you could get. It's the most conservative case. Hunt came around in 1999 and said, well, those assumptions that Glover and Balmer used aren't really reasonable. We typically don't have a fully penetrating river. So let's take that into account. So Hunt's scenario is in the bottom middle, and his stream only penetrates just a little bit of the way into the aquifer, and it has this semi-pervious layer. That semi-pervious layer has a stream bed conductance, what I'm calling C, and that's the only new parameter. But in this case, water can come from the aquifer. It can even come from the other side of the river. So less water is coming from the river than it was in the Glover-Balmer case. And that's the equation shown on the bottom right. You can see the Glover-Balmer term, then minus this other term that accounts for the impervious, well, the semi-pervious nature of the streambed sediment. And what that looks like graphically is shown here. The bottom axis, horizontal axis, you could think of as a dimensionless time, and the vertical axis is dimensionless stream depletion normalized by the pumping rate. And then this parameter has to do with the stream bed conductance. And when that parameter is infinity, that's the Glover-Balmer solution. So at early times, you have hardly any stream depletion. And over time, you start to level out at a stream depletion equal to the pumping rate. But it could take a long time. When you do have some, this semi-pervious layer, some resistance to flow across the stream bed, when you take that into account, then the lower the hydraulic conductivity is of that stream bed, the lower the stream bed depletion, or the stream depletion is. And you can see that by these lines. As this CL/T parameter decreases, the stream depletion also decreases. So those are two analytical solutions. And then there are others that deal with changes in the geometry, like a bounded aquifer, wedge-shaped aquifer, leaky aquifer, others that deal with different kinds of streams, not an infinitely long straight stream, like a V-shaped stream, two parallel streams, and many more. A lot of people have looked at special cases with analytical solutions. The other way to estimate stream depletion is a numerical approach. What we would typically do is use the Glover-Balmer method and get a first cut at stream depletion. And then if that stream depletion exceeds our limits, then we'll go with a more robust way, some way that we could take into account the actual geometry of the aquifer, the actual geometry of the river, and so forth. And I've listed here the steps to do it numerically. You would create a numerical model of your aquifer and river system, and then run one simulation without pumping and record the exchange of water between the aquifer and the river. So that's, this is the equation we looked at a couple slides ago, and this part is what we would do with that first simulation. This is the head without pumping. So we would look at the exchange across the riverbed when we don't have any pumping. And then we would run a simulation with pumping at a known well location. And we would get our new head distribution, because now head is going to change due to pumping. That will create more drawdown at the river. And we will look at the exchange of water between the aquifer and the river in that scenario, and then take the difference between the two. So this is something that we would do if we want a more accurate representation than we can get out of an analytical solution. And I have an example here just showing schematically what we do. So this is, now I overlaid a grid on top of the aquifer, and on the left, I have some head distribution without pumping. This is a losing river, so water's flowing from the river into the aquifer. You can see that Q sub S and the arrows there. On the right, we're showing the same thing with pumping. So the original head distribution is the lighter blue, and then with pumping, we have this darker blue. So there's more head difference between the river and the aquifer, which creates more exchange between the river and the aquifer, so it increases stream depletion. Oops. Now the adjoint approach, let me come back here. The adjoint approach is a different way of running this same numerical simulation. So what we can do with what I've just shown here is, if we don't know the location of the well, let's suppose we want to install a well, but we want to put it someplace where the stream depletion won't be excessive. It will meet whatever the state limitations are. And perhaps I don't know where to put that well. I want to test many different locations. So what I would have to do is run one simulation for a well at one location, and then do that calculation shown at the bottom, run another simulation for a well at a different location, and so forth. And I'd have to run multiple simulations. Every possible well location would be another simulation. This could get computationally expensive. Some of these models could be very sophisticated, take a long time to run. And if you have to do many simulations, it's really inefficient. But the adjoint method is a way of modeling from the point of view of the river. And I'm just going to show you schematically what that is on this next slide. So here we have the river. What we do, instead of saying, I'm going to pump water out of a well, so I'm going to change the head distribution driven by pumping at that one location. We think of it rather as, I want to not decrease the flow in the river by more than a certain amount. So I'm going to put a perturbation at the river of that allowable amount, and then allow that to distribute through the aquifer. And I'm just going to show here a little bit of an animation where, at some later time, that initial perturbation gets distributed into the aquifer, and then at some later time, that gets distributed farther. And what I'm showing here with these arrows is what we call the adjoint state. And all this is that initial perturbation distributed through the aquifers. So we're looking at what is that perturbation at a particular location at a particular time. And it turns out there's a lot of math to derive this, and I won't go through that at all, but it turns out that if we run a simulation like this, we get this adjoint state at every location at all times with one simulation. We integrate that over time, and that gives us our stream depletion. It means it's a lot more efficient if we want to figure out where to put a well. So we could look at this and say, well, I need my stream depletion to be less than a certain amount. And with one simulation, I could find all those locations where it's less than that certain amount. I'm going to show in the next slide an example, just so you could perhaps have a better idea of what I'm talking about. Oh, actually, I have a slide here of the equations. I'm only going to show these to emphasize that we use the same model. So I use ModFlow a lot. We can use ModFlow to solve the general forward kind of simulations, and we can also use it to solve the adjoint simulations. What I'm showing at the top is the equation of groundwater flow. We have the accumulation term. This is the Darcy's law term. This is the exchange between the river and the aquifer, and this is our pumping. In the adjoint equation, we have, again, the exchange, the accumulation term, the Darcy's law term. We have a term that looks a lot like the exchange between the river and the aquifer term, except there's a zero here instead of that head in the river. And then instead of the load, the source, or the sink of water at the well, we have this perturbation, this addition of adjoint state, I'll call it, at the river. But the equation is the same for the most part as the forward equation, so we could use ModFlow as well for that. This is the example that I wanted to show. So on the left, we're looking at, this is up here, you can see a map. This is the state of Arizona, and we're looking at an aquifer that spans between the very southern part of Arizona and the northern part of Mexico. This is the San Pedro River through here, and this is an important aquifer, partly because there's international border that it goes across, and partly just because of the habitat of the various species that live there, the Native American reservation that needs water, and there's many reasons why this is important. So there's a model developed by the USGS that looked at stream depletion due to pumping in this aquifer. And what I'm showing on the left is at any block, and you can kind of see the size of the grid blocks here, but for any block, it's showing if I pump water out of a well at that location for 10 years, how much of the water that I pump out comes from the San Pedro River. So right here near well, let's come down to this part. Right here near the San Pedro River, almost all of the water, if I put a well very close to the river, almost all of the water that I pump will be coming out of the river. And if you go far away, down here at the southern extreme of the aquifer, if I pump water out of a well here, almost none of it will come out of the river. And you can see, in between, there's a range from 0 to 100% of the water coming from the river. So this simulation was done for just with one model layer on a 1 kilometer by 1 kilometer grid. And I looked at 1,530 different locations. So I did 1,530 different simulations to get the forward simulations. And that was a total of about 6 hours. The adjoint model is shown, the results of the adjoint model are shown on the right. So this is the same location, the same aquifer, but in this case, I didn't run individual simulations for each possible well location. I just put in the perturbation along the river, like I showed on the previous slide or two, and allowed that to propagate into the aquifer and let that propagate for 10 years. In one simulation, so this took just one simulation, I had a coarser grid, 0.25 kilometers by 0.25 kilometers. I used 5 model layers, so it's a more accurate model because we're looking at the vertical discretization that wasn't looked at in the simulations on the left. And that whole thing took just about 9 minutes. So it took a lot less time, and we got a lot more accurate information. And you'll notice here in this part of the river, it matches pretty well between the forward and the adjoint simulations. Up in the northern part, there's less of the match is not as good, but that's because of the accuracy of the forward model. We had to do it on a coarser grid, and it becomes less accurate the more coarse the grids are. So we got a much more accurate model with the adjoint simulations with a lot less time. Okay, so a quick summary of the estimation methods. The analytical solution there are several of them, but they're applicable for simplified geometry, simplified hydraulic conditions. They tend to overestimate stream depletion, so they're a good screening tool. If you want to keep your stream depletion under a certain amount and the analytical solution shows that it is under that certain amount, then you're good. You know that it won't be more than that. If that's not the case, you want to run numerical simulations and do more accurate models and fewer assumptions. If you have multiple well locations that you want to consider, you have to run one simulation for each possible well location. So the forward numerical approach is efficient if you have just a few wells, but if you have lots of well locations you want to consider, then the adjoint approach is going to be much more efficient. All right, so we'll move on then to talk about some of the recent advances from my students and some of the work that I have done. The first one, we'll talk about sensitivity of stream depletion to stream bed properties. So at the top, again, you can see the picture that we looked at earlier. What we're looking at in these plots on the right are how is stream depletion changing when the hydraulic conductivity of the stream bed sediment changes. So we're using the aquifer on the bottom left is the plan view of what we're using. We're looking at stream depletion due to pumping at either well A or well B. Well B is farther from the river. Well A is closer to the river. And the top right, the top left plot is showing showing stream depletion due to pumping at well A for an aquifer hydraulic conductivity of 5 meters per day, and for a stream bed hydraulic conductivity that ranges from 10 to the minus 3.75 meters per day up to 10 to the minus 1.5 meters per day. So I'm sorry, I'm saying it wrong. From 10 to the minus 4 meters per day, that's this lowest line down here, to 10 to the plus 3 meters per day, that's the top line on top. So if the hydraulic conductivity of the stream bed is really low, most of the water that the well is pumping will come from the aquifer because it's hard to get water from the river to cross the stream bed. If the stream bed hydraulic conductivity is very high, we'll get a lot of water from the stream bed because it's easy for the water to cross that stream bed to get into the aquifer. For the well farther away, well B, we get lower drawdown. I'm sorry, we get lower stream depletion because the well is farther away. I think that's relatively reasonable. What we're looking at in the bottom two plots is just a different hydraulic conductivity of the aquifer. But what I really want to focus on is these dashed lines right here and one right here. And these are the lines for hydraulic conductivities of 10 to the minus 3.75 meters per day up to 10 to the minus 1.5 meters per day. That's really where we have the most variability in stream depletion. If you get any higher than that, there's not much change in stream depletion, no matter how much hydraulic conductivity of the stream bed changes. So we can go, this goes all the way up to 10 to the third, so 4.5 orders of magnitude higher, and you don't really get that much change in stream depletion. So what we found here was that there's a range of stream bed hydraulic conductivities for which the aquifer, or for its stream depletion is sensitive to the stream bed hydraulic conductivity, K sub S. Below that range, you get hardly any stream depletion, and above that range, the stream depletion doesn't change very much at all. So that was one of our findings. Another thing we looked at is what happens when you have spatiotemporal variation in the stream bed hydraulic conductivity. So a lot of the numerical simulations assume that the stream bed has one hydraulic conductivity throughout the whole domain of the model. And that's not really how things work in nature. And what I'm showing on the left are two different representations of hydraulic conductivity in that same river. Under the left is showing high flow conditions, the right is showing low flow conditions. Under high flow conditions, you have scouring in the riffles, so in this area here, and deposition of sediment in the pools. So you'll get higher, oh, I have these, I knew there's something wrong here. Yeah, these are incorrect. So you get a higher hydraulic conductivity in the riffles when you have high flow, and a lower conductivity in the pools when you have a high flow. Then looking on the right plot, it's reversed under low flow. Under low flow, you'll have deposition in the riffles, so lower conductivity in the riffles and higher conductivity in the pools where you have scouring. So this is something that isn't taken into account in most numerical simulations, and certainly not in most of the analytical solutions of stream depletion, but it could make a difference. So what we're looking at on the right in the plan view plots is showing if we have like the top is showing if we have a low hydraulic conductivity of the stream bed. Under low flow, we'll just take a look here. Under these contours are showing the stream depletion, so delta QS over Q. And if we look at a point maybe right here, under low flow, it's depleting, it has a stream depletion of about 0.05. But if we look at that same point over here under high flow, it has a stream depletion about a half of that. So if our state identifies a threshold value of stream depletion, we should be taking into account that there are differences between high flows and low flows because of these changes in the sediment properties. Another thing we looked at is what I call exaggerated stream depletion, and I'll show that on the next slide. So we came up with an analytical solution that relaxed this assumption of homogeneous stream bed conductance. So what we did was look at still a straight river like we have in this conceptual model, but we've allowed the hydraulic conductivity along the river to vary in space and time. So just like what we looked at on the previous slide, where the stream bed had higher hydraulic conductivity in the riffles or in the pools, depending on whether we had high flow or low flow. We did the same thing here, but just on a linear stream. So the blue is showing high stream bed conductance or high stream bed conductivity. The red is low. And what we're looking at here on the left is at time 0, we have high stream bed conductance at this point, low stream bed conductance at that point. At some later time, these colors are still blue at the top, then red, then blue, then red, but not as dark. So you can look at that as being not quite at the upper limit and lower limit of our range of stream bed conductance. And then on the far right, what's labeled C, is if we go through one periodic cycle of this, we get low stream bed conductance at the top, high stream bed conductance, a distance of lambda below that, or lambda over 2 below that. So we get this cyclic variation in space and in time of stream bed conductance. And that's represented by this equation that I have boxed in red. We have cosine functions representing the variation in space and time. So what does that do to stream depletion? We solved the equation. I won't go into this at all, but we solved the governing equation for flow, got an equation for stream depletion, but we could only get it in Laplace space. So we have to do a numerical inversion. And the equation in Laplace space depends on this function d, which is shown down here, but d1 depends on d1 evaluated at other parameters. So this p is the Laplace domain parameter. So the whole point of showing this is to show that we can only get a solution in Laplace space, and it's a recursive, it depends on a recursive function. Not critical for what I'm going to show with the results, which are shown here. So what I'm showing on each of these plots is on the horizontal axis, it's time, so over 10 years. On the vertical axis, it's stream depletion, normalized by the pumping rate, by the mean pumping rate. I guess we only have one pumping rate here, so by the pumping rate. And there are 3 lines on each plot. The solid line is the stream depletion when we have this periodic fluctuation in space and time of the stream bed conductance. The dot dash line is when the stream is homogeneous and it has only the lowest hydraulic conductivity, the lowest stream bed conductance. And then the dashed line is what we would get if we have a homogeneous stream with the highest stream bed conductance. And I think this makes sense here. If you have low stream bed conductance, it's hard for water to flow across the stream bed. So you get low stream depletion. Most of the water comes from the aquifer. If you have high stream bed conductance, water can flow more easily across the stream bed. So you get higher stream depletion. And if it fluctuates, if the stream bed conductance fluctuates in space and time, you get this fluctuating pattern. So I have 3 different cases here. The parameters used in them are shown on the bottom, but the point of showing these 3 cases is that you can get some different results and maybe some unexpected results. So case 2 here happens to show that if you have stream bed conductance that varies in space and time, not only do you get that fluctuating pattern, but you actually get stream depletion that at certain times exceeds what you would have if you had just the high stream bed conductance value, and falls below at times what you would have if you had just the low stream depletion or stream bed conductance value. So we call this exaggerated stream depletion. And the reason for that, I have a couple things to add here. The reason for that, this is showing this middle plot is showing the conductance at y=0 as a function of time. And so it varies as a cosine. It varies from the highest value to the lowest value. And then the plot below is showing drawdown at y=0 in the stream as a function of time. And what's happening is that, let's take this point right here, this time at 5 years. This is a point where the stream bed conductance is high, but the drawdown is actually lower than it would be if we always had the high stream bed conductance. And that means that there's less of a gradient, more of a gradient, which drives more water out of the river into the aquifer. So it's a trade-off between the amount of drawdown you have in the aquifer compared to the variation in the conductance of the stream that gives us this exaggerated stream depletion. And then the plot on the far right is showing another unique feature. When we do have this exaggerated stream depletion, there are certain scenarios when the well is close to the stream, for example, where you actually get stream depletion that exceeds the pumping rate. And this occurs because, again, you have this different drawdown. The drawdown is changing over time, just like the stream bed conductance is. So there are actually times where you can get more flow of water from the aquifer from the river across the stream bed into the aquifer than you have of the pumping rate. This plot, I won't go into much detail in here, but this plot is showing for different values of this dimensionless stream bed conductance, different values of the spatial period of the stream bed fluctuations, and then this is the dimensionless time, dimensionless period of the fluctuations in time. What this is showing is the difference. It's the amount of stream depletion above what you would get if you had just using the hydraulic conductivity of the stream bed at its highest value. And the dark shades here are where you have exaggerated stream depletion. As the shades of blue get lighter, you have less exaggerated stream depletion. And the ones that are outlined in red are where you have excessive stream depletion. So stream depletion greater than the pumping rate at some time, not at all times. So you can see that for a wide range of the parameter space, you don't have exaggerated stream depletion or excessive stream depletion. So this is more or less it's less important. But if there is a case where you're pumping more water out, or your stream flow is depleted by more than your pumping rate, then it could really impact the flow rate in the streams. Okay. We also looked at if you have temporal fluctuations in pumping rates. And again, we came up with an analytical solution. What we did here, we also kept the stream bed conductance varying in space and time, but now we also included a temporal fluctuation of the pumping rate, which is not unusual. We do all of our estimations of stream depletion based on a continuous pumping rate, but more often the pumping is to provide water for irrigation, and we irrigate in the summer during the growing season, not in the winter. So we do have some sort of periodic fluctuation, and we have the same kind of solution, a little bit different functions. And what I want to point out here, the purple is the solution that has spatiotemporal variation in the stream bed conductance and also temporal variation in the pumping. And there's a deviation here between the maximum stream depletion that you would get under that case versus the maximum stream depletion you would get assuming a continuous pumping rate and a homogeneous aquifer, which is what we always do in our simulations. And then I have a plot here that shows the value of that deviation for different parameter sets. So this one shows a little bit more blue, a little bit more significance of this temporal fluctuation. And so I think what this is emphasizing here is that if you use just the steady pumping rate, there are certain times of the year where you may actually deplete the river more than the allowable amount, but you wouldn't have predicted that if you didn't account for that in the simulations. And the last one I want to look at is cumulative stream depletion. So this is when we're looking at the cumulative volume of water that has crossed the streambed sediment from the river into the aquifer. And it's really, we're just integrating stream depletion over time to get a volume. And we did some analytical solutions, simply integrating the Glover-Balmer and the Hunt solutions. And this is our analytical, our plot of the analytical solutions. Looks kind of the same as the plot I showed of the stream depletion by Hunt earlier. And what I want to show is this application. So this was from the Gloucester River in New South Wales, Australia. What we're looking at on the left is just our model domain. The second plot from the left is the head. So highest head down here in the south, lower head in the north. So the river is flowing from south to north. The groundwater also is flowing from south to north. And then what I'm looking at on the right, there are two plots. The first one is the result of many forward simulations. So we put a pumping well at each location, each grid block, ran a forward simulation and looked at the total exchange or increase in the volume of water that flows across the river. And then the one on the right is the adjoint result. And I guess the main idea to emphasize here is that the adjoint solution was just one simulation. The forward solution, I don't have the number of simulations shown here, but the forward simulation was, we'll say probably 1,000 more simulations because there are that many grid blocks, and we still got about the same answers. So again, the adjoint simulation is more efficient. And what I also want to emphasize is that we're able to look at how much of the volume of water pumped would come from the river when we look at this cumulative stream depletion. Okay, so I'll just summarize with this slide. We're looking at stream depletion, which is how we quantify the reduction in the flow rate in a river due to pumping from a well that's hydraulically connected to the river. We can use analytical solutions to estimate it. They have a lot of assumptions, so they're better as screening tools. If the analytical solution shows us that we have more stream depletion than the threshold, then we probably want to run a numerical solution. And if we have multiple well locations to consider, the numerical solution is more efficient if we do the adjoint approach. And then some of the recent advances are highlighted below. So stream depletion is not sensitive to the full range of values of stream bed conductance. It's only sensitive to a small range. And the spatiotemporal variation in stream bed conductance can produce exaggerated stream depletion or excessive stream depletion that we should take into account when we are coming up with whether or not we meet these these stream depletion thresholds. And I will stop there. So thank you for your attention, and I'm happy to take any questions.
Thank you so much, Dr. Neupauer. I don't know if there are questions in the chat.
No, there are no questions in the chat yet. So
Uh-huh.
please, to everyone who's watching this seminar, please feel free to leave your questions. It can be in English or in Spanish, and I can translate the questions to Roseanna. I have a couple of questions, if I'm allowed to ask. So first, I want to thank you, Roseanna. This is super interesting work, and this a very interesting topic, by the way. So you were showing lots of results analyzing the sensitivity of your simulations to the hydraulic conductivity of the sediments. And I was wondering if you have conducted additional experiments looking at other parameters of your system that perhaps could be relevant, like sediment thickness of the river width.
Yeah, those, any parameter that goes into that conductance. So we had the hydraulic conductivity, the sediment thickness, and the width of the stream could all affect the, any uncertainty in those could affect the sensitivity of the simulation. But the hydraulic conductivity varies the most. So it could vary over orders of magnitude. The sediment thickness, maybe that varies over a factor of, the uncertainty could be maybe a factor of maybe 3 to 5, maybe an order of magnitude, but probably not even that high. And the width of the channel is definitely not going to vary by an order of magnitude. So the most sensitive one is going to be the streambed hydraulic conductivity. And that's one that is hard to measure. It varies. Now we looked here, ran simulations for it varying along the flow direction and in time, but it also varies across the channel. So there was a study done by some people at NC State, North Carolina State, that they just went out and measured streambed, I think it was hydraulic conductivity across a channel at several different times over the course of a year, and it varied a lot. So we're, even with the types of heterogeneity that we're allowing for, we're still really oversimplifying.
Okay, cool. Thank you, Roseanna. So there are no questions in the chat yet, but I have more questions.
Okay.
So in one of your last slides, you were showing this analysis of what happened if you have temporal variations in the pumping rates. And I was wondering how realistic are the assumptions of your analytical form, like a sine and cosine function or something like that. Like, have you, or are you planning to conduct additional experiments with different assumptions of how these pumping rates may change depending on the system that you're studying?
Yeah, so in the results I showed there, we wanted to get an analytical solution. So we had to use a simple function like a cosine function. And I think that's not that unrealistic, because we'll typically have an annual fluctuation, or there'll be an annual cycle. So pumping will be more during the growing season and maybe zero outside of that. So it probably is not perfectly cosine, but it could, in many cases, be approximated that way. One thing that, well, if it is something more complicated, then we could use numerical simulations. And the one thing that I'm currently working on is coming up with the adjoint solution for these time varying pumping rates. And what it shows for us is that we run one adjoint simulation, and then we do some post-processing with this, whatever the pumping function is. So you don't have to put that into your numerical simulation, which is really convenient. But also to look at how things are going to change with the change in the growing season. Maybe the growing season is starting earlier or later, or the timing of snowmelt and the growing season are no longer aligned because of climate change. So you have to pump earlier than you would. So those kinds of effects couldn't be conducted with the analytical solution, but definitely could with the numerical solution. So it ties in with some of the work that I'm currently working on.
Cool. That jumps into my next question, which is related with the river flow. You were just mentioning that there are connections with hydrological processes happening at the surface, such as snowmelt. So numerical models open the possibility to incorporate all these processes and the connection between what's happening in the surface and the groundwater. And I'm wondering if what are the next steps for you or for the hydrology community in terms of connecting stream depletion with what's happening in the surface in the climate change context?
Yeah, and that's where it becomes really critical. I think you said you're on a 5-year drought or something like that, and we have
13 years.
13 years. Okay, yeah, I knew it was a big number, but and same thing here. So we're all dealing with less surface water, which then I think it has to get made up with, unless we reduce our usage, has to get made up with groundwater. So there's really this coupling that is important to understand. If you can't necessarily pump more groundwater because some of it will come out of the river, which is already low. So you're trying to protect that. So I think it really then becomes an optimization problem. But I think in that sense, the adjoint method is really useful because you can decide, okay, let's turn this well off, the one that's nearby, because that would lead to more stream depletion, and use one farther away because that will lead to less stream depletion. So it's, I think also the heterogeneity that we were talking about, you also add on top of that the non-stationarity of the surface water resources, and everything just creates the additional complexity. So I think the coupling of the simulations of groundwater, surface water, and running, using it as a tool for optimization, rather than just saying, okay, this is the stream depletion we're going to get, but rather, if we want to protect this river or reservoir, whatever it happens to be, where can we be pumping? And then, of course, incorporating the uncertainty. So yeah, it's complicated. There's going to be a lot of very interesting hydrology done in the near future, I think.
Cool. Awesome. Thanks, Roseanna. I don't know, Nico, if you have any further questions?
No, I don't.
No, because I have one more question for Roseanna.
Go on.
And this is related with what could be associated with stream depletion, because so the definition is related with the reduction in flow rates, and I was wondering, what about the contaminant transport of contaminants? Can this be included in this type of approaches? Is it something that are you exploring?
Yeah, I do a lot with contaminant transport, but not combined with stream depletion. So yeah, are you thinking of contaminants in the groundwater that could get into the stream, or
vice versa?
Or vice versa, yeah.
Yes.
Yeah. That ties in a bit to some of the work I did a few years back with riverbank filtration. So you actually use a pumping well, you use river water, but you extract it out of a pumping well, so it passes through the aquifer as a filter. But no, we really haven't looked at contamination And especially when you're looking at these, these cyclical patterns, and there'd be times where you'd be drawing more water in, so perhaps drawing more contamination, or maybe there's a timing that at certain times of the year, there's more nitrogen or less nitrogen or whatever it happens to be that could produce contamination. That's interesting, especially around the agricultural sites or the farm sites where they're either using pesticides or there's animal waste that could get into the river. So perhaps that's a future direction.
Yes, that's topic for future papers.
Yeah.
Okay, thanks a lot, Rosanna.
Thank you.
Okay.
So thanks again, Dr. Roseanna. The university will have a recess on September. So the next session will be on September 29th with Dr. Lieke Melsen. And the title of her presentation, it will be, "It Takes a Village to Run a Model." So we invite you to join on September 29th. So that's it. Thank you, Dr. Neupauer, again, and have a good afternoon.
Okay. Thank you.